Section 7.1 is the standard normal curve. We've looked at normal curves before. Do y'all remember? Normal curves have this general shape. They're symmetric and unimodal. And we said that the mean is in the middle and then the standard deviation goes out so far. And I'll have a picture in a little bit. So if I add one standard deviation to the mean, I go this way, and then another standard deviation goes out here, so forth and so on. But they're symmetric and unimodal, with the mean being at this high point right here. Any general normal distribution is defined by the parameters for the mean and the standard deviation. Mu, remember this Greek letter mu, stands for the mean, and this lowercase Greek letter sigma stands for the standard deviation. You can define any normal distribution for any given mean and standard deviation that will have this general shape. The total area underneath this curve has got to be equal to 1. Today we're going to look at a standard normal distribution where the mean is equal to 0 and the standard deviation is 1. If that's the case, the mean would be at 0, and if we add one standard deviation as we go out, these would be the numbers along the bottom at each of these different intervals. The mean is 0 and the standard deviation is 1. This was just to refresh your memory of what a normal distribution looks like, because that's what we're going to be dealing with in Chapter 7. Objective 1 is to use a probability density curve to describe a population. Let's begin by defining what a probability density curve is. The following figure presents a relative frequency histogram for the particulate emissions of a sample of 65 vehicles. Along the vertical axis we have the relative frequency, and then here's the count for the particulate emission for 65 vehicles. If we had information on the entire population containing millions of vehicles, we could make the rectangles extremely narrow. The histogram then would look like a smooth curve, and we could approximate this distribution, and this function here that's outlined in red is what we call the probability density curve. For a normal distribution, the function that we could graph to get this curve would be our probability density curve for a normal distribution. There is a relationship between areas and probability density curves. First of all, the total area under the curve has to be equal to 1 because that area represents a probability. That area under the curve is synonymous with the probability of a function, and if I look at the total area under the curve, what I'm looking at is the sum of all of the probabilities of my sample space. And we said that that sum of all of the probabilities has to be equal to 1. So this area is equal to the proportion of the population that's between the left bound and the right bound of the shaded regions. This is the probability that a randomly selected value from the population falls between these two numbers. Areas are synonymous with probabilities. Keeping that in mind, we can go down to this next graph that illustrates the point that the region above a single point has no width, therefore it has no area. So if I wanted to ask you what is the probability that x is equal to a specific number like we did with the binomial distribution for discrete data, we could get an answer with discrete data, but with continuous data, and normal data is continuous data, we can't find an area under a point because the area under a point is a line, and a line doesn't have area. So we would say that this probability is equal to 0 for any number. This means that the probability that x is between two numbers is the only probability that we can find. I can find an area or a probability between two given numbers. So in this section, we're not going to be finding the probability that x equals 4, like we did with the binomial distribution. We're going to be looking for the probability that x is between 2 and 3, but probability that x is greater than 5, those kinds of things. Objective 2 is using a normal curve to describe a normal population. First of all, normal curves are used to represent continuous data. Binomial distributions were used to represent discrete data. Probability density curves come in many varieties depending on the characteristics of the populations that they represent. Many important statistical procedures can be carried out using only one type of probability density curve called a normal curve. We like for things to be normally distributed. Remember, we said that a normal curve is unimodal and symmetric, so they have this shape. The number right here in the middle would always be the mean of our distribution. Some properties of a normal curve are that the mean will always be located at the peak. The standard deviation tells you how spread out your data values are. So for this graph right here, this is a normal curve where the mean is 0 and the standard deviation is 1. If we keep the mean at 0 but increase our standard deviation, remember the standard deviation is a measure of spread. If the standard deviation is larger, our distribution is going to be larger. It's going to be shorter and more spread out because the area under both of these has to be equal to 1. If the mean is 0 and the standard deviation is 1, I have this curve where the area is 1, the total area under the curve. If I take that area and I spread it out, it can't go as high. This shaded area is going to be the same for both of these. Also, if you have a normal distribution and the mean is different but the standard deviation is the same, for example, here the mean is 0 and the standard deviation is 1, but for this graph the mean is 5 and the standard deviation is still 1. So our spread is going to be the same for both of these. It's just that we take this first graph and we shift it over to be centered at 5 in order to get the second graph. Properties of normal distributions. We have looked at this before when we were studying measures of spread and measures of relative standing. Normal distributions follow what's called the empirical rule. You'll also hear me refer to it as the 68, 95, 99.7 rule because that's what these numbers are right here. These numbers represent the percentage of data that falls within one standard deviation of the mean. So right here, if I were to add a standard deviation to the mean, I stop right here. And if I were to subtract a standard deviation from the mean, I would stop right here. So between these two numbers, I would have 68% of my data. Likewise, if I moved out 2 standard deviations from the mean, meaning 2 standard deviations above the mean and 2 standard deviations below the mean, I would see that I have 95% of my data. And then if I went out a 3rd standard deviation, I would see 99.7% of my data fall within 3 standard deviations of the mean. This is called the empirical rule. It doesn't matter what the mean and the standard deviation are. If your distribution is normally distributed, these percentages will always hold for these values. Now the notation that I use to describe or define a normal distribution is this tilde right here means that we have a distribution. Capital N means that it's a normal distribution. And then I tell you what the mean and the standard deviation of that distribution are. For a standard normal distribution, the mean will always be 0 and the standard deviation is 1. When we have a standard normal distribution, the numbers along the bottom here would be 0, 1, 2, and 3, and then -1, -2, and -3. So for a standard normal distribution, my mean would be 0. The mean plus 1 standard deviation is 1. The mean plus 2 standard deviations is 2. The mean plus 3 standard deviations is 3, and so forth and so on. Do y'all remember me talking about the Z-score formula where we said Z is equal to X minus the mean divided by the standard deviation? Let's use this formula to verify that the numbers that I have written in green are accurate. So let's convert this normal distribution into the standard normal distribution. If X is equal to the mean, then I would drop in a mu in place of X in that formula. Z equals X minus the mean divided by the standard deviation. Because I said X was equal to mu, I would replace X in this formula right here with mu. And what is mu minus mu? And 0 divided by the standard deviation is 0. Notice when X was equal to mu, I said that the standard normal distribution is 0. Let's pick another one. What if X is equal to the mean plus 2 standard deviations? Then we start with the Z-score formula. Z equals X minus the mean divided by the standard deviation. And in place of X, I'm going to drop in mu plus 2 sigma. Well, what's the mean plus 2 sigma minus the mean? These two means are going to cancel out, but I've got 2 sigma divided by sigma. And the sigmas will then cancel out, and I'm left with 2. Well, look at what I said this was. The mean plus 2 sigma, when I convert it to a Z-score, is equal to 2. Notice whenever we're referring to a standard normal distribution, we use Z for our variable. RV stands for random variable. Anytime you see me use x for a random variable, I'm talking about some other normal distribution where you have to be told what the mean and the standard deviation are. So that's one way you can tell if you're talking about a standard normal distribution or any old normal distribution, is by what they're calling the random variable. If they call the random variable x, it's just a normal distribution, but if they call the random variable z, then it's a standard normal distribution. Standard normal just means the mean is 0 and the standard deviation is 1. Now, I'm going to teach you how to find probabilities and z-scores using your calculator. I'm not going to teach you how to do this using tables. I used to teach it using tables, but people would get more confused than what's necessary, and our calculators already have this pre-programmed into it. What we're going to use to find the area under a standard normal curve is something called the normal CDF. If you remembered working with binomial distributions, we had something called a binomial CDF. CDF just stands for a cumulative distribution function. In that normal CDF, you're going to need to put in your left bound, your right bound, your mean, and your standard deviation. If you have the older operating system on your calculator, this is what you need to remember, the order of these numbers separated by comma. Those of us with the newer operating system, when we hit second vars and then it's number 2 for the normal CDF, your home screen will prompt you and ask you what is your lower bound, what is your upper bound, what is your mean, and what is your standard deviation. So the newer operating system prompts you what numbers to put in. If you have the older operating system that doesn't do that, you've got to write down the order in which to put numbers in. The domain for the normal distribution is from negative infinity to infinity. So this graph, even though it looks like this comes down and stops at some point, theoretically it's still going off to negative infinity this way and to positive infinity this way. So when I look at the shaded region and I want to find the area of this shaded region, if my region is going off to the left, my left bound is going to be negative infinity. The problem is we don't have a negative infinity button on our calculator. How we overcome that is we just use a really small number like negative 100 or negative 1,000. Or negative 1,000,000 if you just like typing zeros. If your area goes off to the right, you would use a really large number for your upper bound. And we're going to go through some examples now where we actually do this. I also want to point out the definition of z-scores, and I don't think that it's given right here. Z-scores are simply the number of standard deviations a particular data value is above or below average. If we look back here, we said average is the mean, that's 0 in the middle. Our z-scores are positive when we go off to the right because we're above average. Our z-scores are negative off to the left when our data values fall below average. So if our data values are above average, we have positive z-scores, and if they're below average, we have negative z-scores. And I've already mentioned how we find the area with the TI-84 is we hit second vars and then select number 2, the normal CDF. And let's use that now to find the area to the left of z equals 1.26. Whenever you're given these problems, you want to have a picture. If one is not provided, you draw the picture. And we'll see some examples where we actually have to do that. The way this would look in symbols is I would ask you what is the probability that z is less than 1.26. This is saying the same thing as what I have written out in text. In our calculators, we would go to the normal CDF and we would use what for our left bound. Looking at the shaded region, what's the leftmost part of this shaded region? It goes off to negative infinity, doesn't it? What did I tell you to use whenever this goes off to negative infinity? Negative 1,000. Or let's say negative 100. It'll work with 100. And then your right bound is the rightmost part of the shaded region, and that's going to be 1.26. Because this is a z-score, I know that my mean is 0 and my standard deviation is 1. Now before I even grab my calculator, do I expect this probability to be greater or smaller than 0.5? Greater, because remember, there's symmetry with these graphs. Exactly halfway is this mean right here. So this is going to be greater than 50%. Let's go to our calculators. And we said we hit second, vars, number 2. The left bound your calculator calls the lower bound. I call it left because it tells you what side of the shaded region to look at. This is going to be a negative 100. You have to use the negative button down here, not the subtraction sign. You'll get an error message if you use the subtraction sign. Your upper bound is your right bound. That's 1.26. The mean is 0. The standard deviation is 1. So we put that on our home screen and we hit enter, and it looks like this, and that gives us 0.8962. And that would be the area of the shaded region. What this represents in words is the probability that z is less than 1.26 is 0.8962. Now we're asked to find the area to the right of z equals negative 0.58. Once again, do we expect this probability to be bigger or smaller than 0.5? Here's the halfway point. Do I have more than half of this graph shaded? Well, there's 50% over here. There's another 50% over here. So yeah, I'm going to have more than 50%, more than 0.5, because more than half of this graph is shaded. The blue region here represents the shaded region. This line here cuts my graph in half, where 50% is to the left, 50% is to the right. More than half of this is shaded. So I'm expecting this to be greater than 0.5. The way that I would express this in symbols is the probability that z is greater than negative 0.58. The way I would do this on my calculator is the normal CDF, where the left bound is what? Negative 0.58. Now the rightmost part is trailing off to infinity, but we don't have an infinity button on our calculator, so what would we use? 100 will work. The mean is 0 and the standard deviation is 1. So now we go to our calculator. We'll hit second, vars, number 2. The left bound is now negative 0.58. The right bound is 100 or infinity. The 100 is taking the place of infinity. The mean is 0, the standard deviation is 1, and we put that in our calculator and we get 0.7190. In words, we would say the probability that z is greater than negative 0.58 is 0.7190. Notice, z-scores can be negative, probabilities are never negative. We have that rule that probabilities can only have values between 0 and 1. This negative z-score, when I'm looking for the area to the right, is going to be a number bigger than a half. In this example, we're not going off to infinity. We're actually looking at a probability or a region that's trapped between two numerical values. The way that I would write this in symbols is, this is the probability that z is in between negative 1.45 and 0.42. The way that I would put this into my calculator is using the normal CDF. What will my left bound be? Look at this shaded region. What's the leftmost part of this shaded region? Negative 1.45. What would my right bound be? 0.42. What is the mean and the standard deviation? When we go to our calculator, we hit second, vars, number 2. The left bound we said is negative 1.45. The right bound, or the upper bound, is 0.42. The mean is 0 and the standard deviation is 1, and that's going to give us 0.5892. So the probability that z is between negative 1.45 and 0.42 is 0.5892. Up here we used the normal CDF to find areas if we're given z-scores. Down here we're going to use the inverse norm to find z-scores if we're given areas. Notice I switch what I'm given and what I'm looking for as I switch from the normal CDF to the inverse norm. If you remember from your algebra days, when you have an inverse function, all you do to get an inverse function from a function is you switch x and y. You switch what you're given and what you're looking for. That's why we call this the inverse norm. We switch what we're given and what we're looking for. So for this problem, we're looking for this z-score if this is the area to the left of the z-score. The way that we'll do this is on our calculators, we're going to use inverse norm, and then it's going to ask us for the area, the mean, and the standard deviation. Now this area has to be an area that's to the left of the z-score every time. So for this particular problem, we would use the inverse norm, 0.26, the mean is 0, and the standard deviation is 1. Let's go to our calculators and see what that looks like. We hit second, vars, because that's where our distribution is. If you will look, right under where your calculator says normal CDF, it says inverse norm. So we'd hit second, vars, number 3 to get to the inverse norm. You may want to make a note of that. The area for this problem is 0.26. The mean is 0, the standard deviation is 1, and this gives us negative 0.64. Typically we round our z-scores to 2 decimal places. So this is equal to negative 0.64. Am I surprised that this z-score is negative? No, because what number has to be in the middle on a standard normal distribution? 0, and this is to the left of 0, so I expected to have a negative z-score. My question to you now is, what would we do if I was given this graph where this area was 0.26 and now we're looking for this z-score, and we know this is 0 right here, and our shaded region that I'm told the area for is this region right here. You can still do the inverse norm, but I said that your area has to be the area to the left. If you're given the area to the right, we're going to use the fact that the total area under the curve has to be equal to 1. What I do is 1 minus 0.26 for my area. The mean is still 0, the standard deviation is 1. And when you put that in your calculator, guess what you get? You get 0.64. Remember, there's symmetry about this mean right here. There's symmetry about 0. So if a negative 0.64 gives me an area of 0.26 to the left, a positive 0.64 for a z-score would give me an area of 0.26 to the right. You don't have to think about that and use it as long as you remember that if you're given an area to the right, use 1 minus alpha for your area, where this number right here is what we call alpha. In the future, with what's coming up, that 0.26 is going to be referred to as alpha. Alpha we use for the area, and we're going to be using that in future sections, so I see no need to withhold telling you that that's what that's going to be. Now we can kind of summarize something I've been wanting to point out. And if you're using the pre-printed notes, just write on the back of the previous page if you don't have adequate space here. But I'm going to make us a little table that will help you decide on when to use the inverse norm and when to use the normal CDF. If we know our z-scores and we want the area, we use the normal CDF, where we put in the left bound, the right bound, the mean, and the standard deviation. If we know the area and want the z-scores, we use the inverse norm, where we put in the area, the mean, and the standard deviation. This area is the area that's to the left of the z-score. If you're given the area to the right, we're going to use 1 minus the given area for the area. This alpha right here is just the number for the area. You may want to put this on your formula sheet because it summarizes everything that we've done so far. The keystrokes for this, if you want to put it down, it's second vars 2. For this one, it's second vars 3. Second vars 2 for the normal CDF, second vars 3 for the inverse norm. We've already done this problem. Now let's find this one. Let's find the z-score for this given area. This area right here is 0.68. We're looking for this z-score. Which function do we use on our calculator? Normal CDF or inverse norm? Inverse norm. What will I put in for my area? 1 minus 0.68. The mean is 0 and the standard deviation is 1. I know the mean and the standard deviation because I'm telling you that it's a z-score. Remember, when we're talking about z-scores, it's a standard normal distribution. We go to our calculators and let's hit second vars 3. And for the area, we use 1 minus 0.68. The mean is 0, the standard deviation is 1, and we get a z-score of negative 0.47 because we round it to 2 decimal places. Typically, you'll round your z-scores to 2 decimal places. What if we want to find the z-scores that bound the middle 95% of our data? Now we're looking for 2 z-scores and we've got to find them one at a time. This area right here is what? Well, the area in the two tails is going to be 5% because 95% from 100% is 5%. That 5% is evenly split over these two tails. So 5% divided by 2 is 0.025. This area right here would be 0.025. The area of these shaded regions. To find the first z-score, I would use inverse norm. What would I use for my area? Z sub 1 is this first one right here. What do I use for the area for this z-score? 0.025. It's the area to the left of this z-score that I'm looking for. That's this number right here. The mean is 0, the standard deviation is 1. And when I put that in my calculator, what do I get? Negative 1.96. To get the second z-score, what would I do? inverse norm, 1 minus 0.025, 0 and 1, and that's going to give me what? Positive 1.96. We hit second vars number 3. The area is 0.025. The mean is 0. The standard deviation is 1. And we get negative 1.96. On the second one, rather than go back to second vars, I'm just going to insert 1 minus right here. 1 minus 0.025. And that gives us the positive 1.96. So we've seen how to do several things. Mainly what we've seen is how to find areas using the normal CDF and find z-scores using the inverse norm. And this wraps up section 7.1.